So yes, we have a channel. Basic channel is just specified by a conditional distribution. Like, so you have some x here, like get into the channel, then you have some y there. So how you're going to use the channel is like, okay, of course the y won't be the same as x. So it's like the channel is not non-deterministic, it's probabilistic. So if it's deterministic, then it will be simple. That's basically no channel. So so because it's probabilistic, so there would be like some error. So for example, like we mentioned like binary symmetric channel, maybe just each bit like just randomly flip and so on. So to send messages like through the channel losslessly, so what we will do is that we put in an encoder and decoder. So instead of like sending the message directly, let's say I have a message M there, instead of sending message directly, I first coded the message into some kind of code word. And let's say the code word with length n here, and then at the decoder I receive yn here, and then I try to decode it back. So, and we want this like the message to be recovered perfectly. So probability that m hat is equal to m should be 1, something like that. So and then we say that in this case, the capacity will be like the amount of information we can send through this channel per channel use. So and it's actually given by like IXY. We didn't give a proof yet. We're going to give a proof today. So and it's simply this one. So the capacity is just like that. So it is very reasonable because let's see wait a sec. I guess some of you just okay. So if you think of that, it's really reasonable, right? So the amount of information can send through this channel would be like how much information share among the two ends of the channel. So it would be just the mutual information there, and you can adjust the input distribution to the channel. So you want to just pick px such that like this mutual information as big as possible, and that would be your capacity. And we kind of show like the capacity for like BSC is like, I forgot, it's like 1 minus HP or something like that. Like this is for binary symmetric channel. So let's try an example. Let's try for the another example here, like for Gaussian channel. So for Gaussian channel, we'll have like X going into the channel. Y is basically like equal to X plus some noise there. Let's see, how do I do? Okay. Is equal to X plus some Z, where Z is some Gaussian noise. Maybe I just say, yeah, okay, I can just put sigma square is fine. Maybe just use n there, yeah. And okay, yeah, okay. Anyway, this is the noise power. Okay, it's a little bit, oh yeah, that's fine. Yeah, I guess that's fine. So and for the Gaussian channel, let's find the capacity there. The capacity will be maximizing the, again, the mutual information IXY with respect to PX here. And so, and this will be, I need to improve my handwriting. So that would be like HY minus HY given XY. And then HY plus X, Y is equal to X plus Z, right? So I can write X plus Z here. And then now X is given as a, okay, X is given basically here. If X is given, then the conditional entropy here, you can think of X is just a constant, right? So since X is a constant, you shift the variable, say by something, it's not going to change the entropy, right? So therefore like x plus z given x, this is just equal to h z plus x here. So therefore, I have this one. And now, because the noise here, okay, I didn't write it here. I didn't give it here, the condition, but x and c should be independent. So it's very reasonable, right? Your noise is unlikely to be unlikely to depend on your input there. So therefore, like c given x will be just equal to hc there, because x and c are independent. So I will just have hy minus hz here. So if this is Gaussian, then you remember this is the entropy is just 1/2 log 2 pi e n here. So let's say this is the sigma square there. That's n here, and then hy. Now I need to determine hy. Okay, maybe I just make a small quiz here. So what is maximum hy? And by the way, I didn't put in a required constraint here. For the continuous channel here, if remember that like our entropy will depend on the variance of the signal. So if I have a higher variance, I will have a higher entropy. So if I don't bound this, I don't have an upper bound for the variance of y, then basically my entropy can be like infinite. So then my capacity can go infinite as well. So therefore, like typically what is reasonable is like we should kind of like constrain the power of x here. So let's say x should have power should be less than equal to p, something like that. So then let me repeat my question here again. So what will be the maximum hy given that like this x squared is less than equal to p? Is the question clear?
In here, does the p has anything to do with the probability distribution of x?
Oh no. Okay, sorry. This just notation. I use p because it stands for power, and I use this n notation stand for noise. It's common like in literature, but here there's unfortunately there's some conflict of notation. But p is just stand for power here. It's not probability. Maybe I don't know how I can make it look better. How about write like this? That would be look like a set though. Oh, maybe not even a good idea. Maybe I just here indicate again. This is power. So is that clear? Like I give you 1-2 minutes maybe. Oh, by the way, like it just came to me, like I think I didn't say something clearly just now, like for the midterm. I said like you may Google that. It's in the sense like I just mean that like I have no control for you guys to Google, but I mean like you cannot plagiarize. Oops. Let me. So what I mean is that like you should understand like what's going on. Like what I mean is like if okay, I even shouldn't go into that direction, but you if you get any inspiration online, it should be like you understand the solution and write in your own words, but not that like you just copy and paste or something like that. So it does it make sense? And oh, okay. Anyway, I don't think you will find solution online, honestly. So
When I asked that question, I was more meaning like we're allowed to look up formulas and
yes,
stuff if we don't remember them.
definitely, yeah. So you definitely can look up for formulas and so on. For example, like this 1/2 log 2 pi e sigma square, you may not remember that. That's totally fine. Like to look it up. Yeah. So do you guys have any idea how to proceed for this one for the question here? Are you guys working on that? Okay. Oh, actually, honestly, the question is actually quite simple. Don't think something really complicated, overly complicated. Maybe I give you one more hint here. So when the point here is like under what distribution like y will have like maximum entropy. Oh, you already finished the okay. Yes, actually, I'm asking just the maximum entropy. I guess I still give the capacity. Yes, I think your capacity is right. Almost. Is that? Yeah, I think it's right. It's not almost. It's right. Yeah. So maybe I will just move on then. Like so, know that like here, of course, I should maximize this hy, right? So this is just constant with, I mean, in the sense that it doesn't depend on px here. So if I want to get maximum capacity, then I should maximize this hy here. And for y, we know that like for fixed variance, the largest entropy will be like the if y has a Gaussian distribution. Therefore, I want y to have a Gaussian distribution. And also like I want y to have the maximum variance. Then in the sense that okay, y will have variance is maximum if like if x is zero mean, right? If x is zero mean, then variance of x will be just equal to the expectation of x squared will be just bounded by p. So I can get like maximum variance of x will be like just equal to p there. And then like maximum variance of y will be just equal to the variance of x plus z there will be just equal to variance of x plus variance of z. So this will be just equal to p plus n. So therefore like, and if variance of y is p plus n, and it can get the highest entropy when y is Gaussian distributed. Or actually, if x is Gaussian distributed, then like y is already Gaussian distributed. So then this will be just half log 2 pi e p plus n, the entropy. So these two got subtract to each other, then I'll just get like log p plus n over n, or like log 1 plus p over n. No, I'm sorry. Like, this notation confused you, but I try to stick with the standard notation. P again, like this small p, this p here is not probability; it's just power. When you send something like through the channel, you can specify how much power you're using for the signal, right? And so, and yeah, yeah, okay. So, okay, this is for Gaussian channel or like AWGN channel, additive white Gaussian channel. Let's see. Should I erase or like let me make another page or something like that. So now let me just rewrite that again. Like for Gaussian channel capacity is like log 1 plus p over n. Oops, why suddenly I cannot write? B, okay. And now if let's consider bandlimited channel. Yeah, Bologna. Yes, but yeah, it's given its Bologna distribution. Yeah, okay. Again, this P is power. Maybe okay. Maybe I use another notation. What? Okay. Yeah. Let me change the notation because I think I confused many of you guys. Let me use a little bit more verbose notation. Maybe sigma. This is bad. I don't know this. I thought this app will be better, but like it just okay. Let me just go back to the regular. Let's see. Okay, let me use the whiteboard again. So again, let me write down this. I use sigma p square over sigma n square. How's that? So probably that would be not confusing at all, right? So that would be like the power, the variance, basically the signal powers will be sigma p square, and the noise power will be sigma n square. This is noise. This is signal. And then let's consider the bandlimited channel. So this is just an extension of like what we talk about here. So band limiter in the sense that it's very common in communications. So I talk about because most likely you saw that equations before, but you probably don't know where that came from. So and I think this is it's good to talk about that. Yeah. So because I think all of you guys, I saw this equation before in basically your first undergrad like communication engineering course, telecommunication course, or communication theory course, or any I don't know how do they call that. So basically, if you have like a band limited channel, so let's say I have bandwidth like this, let's say double band, something like that. This is bandwidth W, and you restrict the signal. It's just lie in this like bandwidth there, and then we want to know what's the capacity for that. And for that, like we'll use the argument from Shannon Lyquist that sampling theorem. Basically, what they said is that like if I have like a signal of bandwidth W, then I will be able to completely recover the signal with 2W samples, right, per second. So if I sample like with 2W samples per second, then I will be able to recover the signal perfectly. So all like these 2W samples can represent the any signal in this band limited, any of this band limited signal. So the other way, the opposite way to think of that would be the degree of freedom of this band limited signal will be basically 2W. We can think of we have 2W individual components that we can play with, independent components we can play with. So therefore, like each of these components, you can add some signal there and transmit through. And okay, I mean, you can control each of these like 2W components there, but as you send this signal through through the channel, then you will have noise there, and the noise typically people write I forgot how do they call it, like N/2 what's it, noise density, I forgot the name. So anyway, let me just call it noise density, and then like the power of the noise will be just basically like N0 times N/2 times 2W. The convention is something like that because we have two bands here. So therefore, like the power will be N0W. This is a power, the noise power here. And because I have 2W components, right? So I can share this, this noise power will be shared among these 2W components. Therefore, like per each component, I will have like N/2, or like let us say N/W over 2W. This is noise per component. And again, each of these components you can think of a separate channel, right? So you can control this component here, and then each of the component basically is subject to noise power N/2. And then we can say like we are going to transmit signal through, again, this band limited channel. We need to specify the power of our signal again. Let's again say the power is like sigma p square. But again, yes, noise power spectral density. Thank you. And again, this sigma p square will be like spread over these 2W samples there, right? So therefore, if I think of like power, I need to really improve my handwriting. Sorry about that. Signal power per component will be equal to sigma p square over 2W, right? So this is noise power per component will be like N/2. Cell power per component will be like sigma p square over 2w. Now, then for each of the component you think of as a separate channel, then the channel capacity will be 1/2 log 1 plus the sigma p square over 2w. This is the power per component over the n log over 2. Oops, why? That will be like the noise power per component. I have over 2 got cancelled. So therefore, this will be like 1/2 log 1 plus sigma p square over n log w. And also like if because I have like 2w of these components, right, each of them think of a separate channel, so the total capacity per second will be just 2w of them. So therefore, like you have like w log 1 plus sigma p square n log over w. I think this is the equation is extremely famous. What's the signal here? Sigma here. Sigma is the standard deviation. Yeah, sigma p square is the noise power. It was a p earlier because I confused everyone, so I changed the notation to sigma p square. Yeah. So I'm sure you see this equation before, but I don't think like you will get a kind of like an explanation why you get this equation. So therefore, like, I think it's a good time to mention this. And actually, one thing is interesting if you think of like, if I let W go to infinity, basically, if I don't have any bandwidth limitation, band unlimited, let's say, then the capacity will be what? The capacity will be, I have W, basically take the limit, right? W go to infinity. Let me write like this. Log 1 plus sigma p square over n log w over 1 over w. So note that like this are both like numerator and denominator and numerator. Oh, sorry, numerator and denominator will go to 0 as w go to infinity. So how do we proceed? So just yes, the L'Hopital's rule. I'm not sure I pronounce it correctly. So you can just take derivative on both like numerator and denominator. So if I take derivative of the numerator with respect to w, then it's like 1 over 1 plus sigma p square over n log w, right? And then I need to take differentiation of this guy. Then I have sigma p square over n log coming up, and then 1 over w, I have 1 over w square coming up, minus 1 over w square. And below also I have minus 1 over w square. So these two got cancelled. Oh, by the way, like this I probably if I assumed here is lateral log. So let me write lateral log. Okay, it's convenient to just change the unit to lat in this case. So it's lateral log. So when I take derivative, therefore it's 1 over this guy and so on. So and then of course in this case the unit will be less here. This is less here. And as w go to infinity, then this term will be gone, right? So basically I will just get like no, how it won't be. Log is like this, right? So it log 1 plus x is not as x go to infinity won't be like, it's very far from that. X is like that. Log 1 plus x is like that. So you can, but anyway, like, so if I use the L'Hopital's rule, I'm not 100% sure. Maybe, yeah. Yeah, but anyway, we are done here already. Yeah. So because you see, like, you get w square or got cancel, like w here, like when W go to infinity, this is actually gone here, right? So it's just like this one here. So this is just, yeah, it's just equal to sigma p squared over n log. This is net, unit is net. But of course, I can convert to bits. Convert to bits is just basically multiplied by log 2 of E. So this is like bits. So one interesting thing to point out is that like even you have infinite capacity here, no capacity, I'm sorry, infinite bandwidth here, your capacity of the channel only increase linearly with respect to your power. So if you increase the power, like, yeah, I mean, for example, if you want to, because most of the channel, wireless channel, everything eventually will be Gaussian like, because every yeah, actually, I'm not sure. Actually, I just say something that may not be correct because I'm not sure. Like it will be Gaussian like, but I'm not sure that will be white in the sense like if I have like if I assume really white like this case white in the sense like the noise power is the same like for whatever frequency, then in that case like you increase the power, of course you get higher capacity, but you only get like capacity proportional to your power, like it's just linearly increasing. So it's not, it seems like a pretty pessimistic result. So you can have like really big power, but like you're only improving linearly. So okay, anyway, any questions for that? Like this is just a, I think it's I like to mention that because I'm quite sure you guys see this equation before, so I just want to explain this. Let's see, what was my, let me take a look of my, oh yeah, I still have a lot to say, honestly. So so I will move on. As I said, like I didn't even prove the, how do I make the little page? Yeah, I didn't even prove the channel coding theorem, right? So I say the capacity is like IXY, something like maximum over PX here. But I didn't say like why we have that. Of course, intuitively it makes lots of sense, but we didn't have a proof for that. So to prove that, of course, there's a forward proof and the converse proof, right? Forward will be saying that like, okay, if I have the weight is less than the capacity. Capacity is defined by that. So if I have like the weight is less than the capacity, then I can find some scheme such that like I can send the message losslessly through the channel. And that will be the forward proof, the forward things we need to prove. And the converse proof will be like something like, it's impossible to send message at a rate higher than the capacity. If I try to send at a rate higher than the capacity, then I will always get some error. So your transmission won't be lossless anymore. So I don't know whether I can go for both forward and converse proof. I will try. If not, I probably will skip converse proof. So, but let's see. So to talk about the forward proof, like we need to revise what we talked about quite some times ago is like the typical sequences. So we say like we have a PX, let's say like a discrete memoryless source, and basically if you sample something from this source, every sequences, so let's say I sample a sequence of length n here, basically all the sequences we sample from this source will be typical. And that's basically just by law of large number. And our definition of typical would be just like px and will be less than, we'll have like, okay, we'll have like probability around 2 to the minus nx. So this is like And the precise definition, like if xn is typical, so we write like this, right? So then it will be, the pxn will be less than 2 to the minus n hx plus some epsilon, oh sorry, minus some epsilon, and bigger than equal to a minus 2 to the n hx plus epsilon. So do you remember all this? So, and also like the number of typical sequences will be around 2 to the nhx as well. It's actually bounded by like the size of typical sequence 2 to the n hx plus epsilon, and this 2 to the minus n hx plus epsilon. I think that's like 1 minus epsilon, something like that. Yeah. And that's for typical sequence. Now, what we want to introduce is joint typical sequence for the proof. So we say something like joint typical, jointly typical. Just think of a same, something very similar, but we have a joint source here, like x and y together. So now we pull sequences together, xm and yn, from this joint sequence. Then you can very naturally, you think of x1 as x and y as a pair, like each time you sample it together. Then we will say like something is jointly typical if we satisfy like p, x, and yn, that satisfies something very similar to the n h x y minus epsilon, and bigger than to the minus n h x y plus epsilon. And also like the size of the jointly typical sequence, or like the number, or I should say the number of like jointly typical sequences by the same token. So I'm not going through, okay, it's like basically exactly the same argument. So it will be like 2 to n h x y plus epsilon and so on. Yeah. Okay, let me write it anyway. 2 to the minus n h x y minus epsilon. So and also like x and y themselves like supposed to be typical as well. So basically like for jointly typical sequences, like I get x, n, and y together, they should satisfy this. They should each other like themselves to be typical, but at the same time like they should satisfy this. But and also like essentially like also by the law of large number, given a joint source, if you're going to pull sequences from this joint source, your sequences will be always jointly typical. It's always going to satisfy this, basically. Now with this, then like we can almost show the forward, but I will try to kind of like extract the core pieces out as a lemma that maybe will be easier to explain. That's something known as a packing lemma. Not packet, it's packing lemma and covering lemma. So they appear like a pair, so very similar. So what they are describing is like, okay, if I'm going to have a joint source here, so let me erase maybe here. As just I mentioned, this joint source like if I pull sequences from this joint source, they will always be typical, always be jointly typical. But what if like I don't actually have the joint source to start with, but I have a fake source that I thought you don't know it's joined, but actually it's not joined. So it's just independent source. They have like the marginal is the same as this marginal of this guy. So I mean like px here is equal to pxy and marginalize y here. And py is also like the same like this, but actually they are independent. So I have x and y and I pull them out. So now in this case, there's no promise that these sequences pulled from these two independent sources will be jointly typical anymore. And actually in general, like they won't be jointly typical. When n goes to be very large, they should not be jointly typical. But the question here, the interesting question here is like, I know they won't be jointly typical, but if I keep pulling out, like if I pull many of these like pairs together, so eventually I probably will get a pair, they will be jointly typical to one another, right? So how many pair will be needed such that like these sequences drawing from like independent sources will still be jointly typical? So is that clear? This is known as the covering lemma. So how many, basically it's trying to address like how many independent sequence drawn are needed such that one of them are jointly typical. And that's very quick. That's very nice. Actually, let's make it a question here. So since Joe already tried it out, so how many of them? I'm actually, I can ask this. Let me finish this other the packing lemma also. The packing lemma is trying to answer a very similar question. Now, this covering lemma is saying that, okay, if I pull out these independent pairs, say, from these independent sources here, how many of them I need to draw until I will find something going to be jointly typical with one another? So of course, it's the probabilistic wise. I mean, like I draw many of them until when suddenly it's like just say, like Kendra mentioned earlier, like it's basically it's actually a phase transition that you suddenly go to another phase. It's like you will have the probability is suddenly like from 0 just shoot to 1. Basically, like you draw sufficient of them, then the probability that like you cover, what we say cover is like that we'll have like two independent sequences are jointly typical to one another, will suddenly go to 1. And in terms of the packing lemma, will be like how many of them are needed, not needed in this case. How many we can draw the same thing so that none of them I want to change the color. None of them are jointly typical. So let's make it this question 2 here, like this one. Actually, let me just give you a hint. Actually, the answer is the same. So this is really a threshold. It's like, okay, yes, that's really good, but I'm not sure you get the, wait a second, like, this is not exactly correct though, but it's very nice. Because you see, like, that is not the number you're giving. This is a 2 to minus n, that would be something like less than 1. So you have basically for both of this question, you have this number, magic number here, maybe I call it M here, this magic number, that if you are bigger than, if you are drawing sequences more than this M, then you can make sure that like, yes, they are jointly typical to one another. And also if you are less than this M, then you are fine. Then none of them will be like jointly typical with one another. And to show the forward proof, we just need this packing lemma basically. There's something known as the weight distortion problem that we'll use the coupling lemma, but we won't talk about that in this course. So okay, I see some of you answered that. Yes, the answer is right, that you need roughly like 2 to n I x y, so many of them. So if you have like, or like if you draw sequences less than this number, then you can make sure that none of them will be jointly typical with one another. So let's see, like let me give a quick proof for that. So I have, oh, by the way, like maybe I just write down union bound there. I don't think I've mentioned union bound like officially, but it's very common. So this is like known as the union bound. If you have like two sets here, two events here, happen A or B, right? A or B will be something like that, right? So probability of having A or B will be equal to probability of A plus probability of B minus the probability of A and B. Sorry, I'm not sure you can read this. Let me just wait. So because of that, then like you will in general have probability A or B will be less than probability A plus probability B. So this is known as the union bound. So you can have like a list of them like A or B or C and so on, then each of them will be less than equal to probabilities, sum of the probabilities. So what so now let's think of like the probability that just think of like a pair, like okay, what's the probability for a pair to be joint typical, that each of them are kind of like drawn independently. So I have like x and y n, so to be typical, that will be equal to, so I can write like this, right? So this is the probability. I can think of like I have like for all the sequences that's typical. So and I just sum over all the probability of them, right? So that's basically just you think of like for each of the sequence, each of the sequence will have certain probabilities and to appear. So therefore, like the probability that like I will have those sequences to be jointly typical will be just like summing over all these jointly typical probabilities of all these jointly typical sequences. And of course, in this case, like x and y are drawn independently, right? So therefore, like px and yn is actually equal to pxn and pyn here. And pxn, we know that like because they are typical by themselves, right? They're typical, so therefore they will have probability. Let's see, I want to have less than like 2 to the n hx plus epsilon, right? Oh, I think it's minus epsilon. And this is like y will be less than 2 to the minus n h y minus epsilon. And again, I have the sum there. And now like, because now this is a constant, then the sum will be just counting like all of this way. So it will be like, this will be less than the total like the total number of like typical Johnny typical sequences will be less than 2 to n h x y plus epsilon. So I can say this is less than that. So therefore, like this will be equal to 2 to the n, let's see, minus n I x y plus v epsilon. So is that right? No, minus v epsilon. Yeah. So yeah, okay. By the similar token, we can say also this probability will be like bigger than equal to like something like that. But anyway, like let's just we know that like that will be upper bound like this. I think I don't need the upper bound. I'm also like I know the probability anyway will be close to 2 to minus nixy. Now so since I have m of them, let's say m, let me call it 2 to the n r, like just call that m. So just rewrite m as like 2 to n r. And I will have, let's say, if I draw like 2 to n r of them, then the probability that any of them are typical will be bounded by like 2 to n r times this guy, right? 2 to minus n I x y minus v epsilon something. And then so therefore just equal to 2 to minus n, let's see, I x y minus r and minus v epsilon. And of course, epsilon, I can make it arbitrary small, then I can just ignore that. So therefore, like as long as like I have ixy is bigger than r, then I will know for sure that like I won't have any of the sequences will be Johnny typical with one another. Yeah. So therefore, as you said, as we just said, like so R should be equal to ixy, and so therefore, like you just have 2 to n ixy as you have all kind of like answer. So that's basically the packing lemma. So again, if I draw less than this, then I'm fine. So I won't have any of the sequences will be jointly typical with one another. Now we can go into the forward proof of our channel coding theorem now. So okay, I don't think I have time for the Converse proof, most likely. So anyway, I will skip that. But that's in the notes. You can look at that if you want. Probably you want, yeah. So and so for the forward proof here again, like so we have the setup again, something like this, right? So we have a channel. Right, so we need to have an encoder. Yeah, it's hard to write. I'm a decoder, something like that, right? I'm a decode back a message, and then encoder. I have like use the channel n times. So I'm going to use the channel multiple times, as we have always written down like this. So for each of the message, I'll just use the channel n times. So we'll send a sequence of xn through the channel, then I receive a sequence yn, and at the decoder, I try to decode it back. So of course, I need to figure out like this encoding and decoding scheme here. So I will have a very simple encoding and decoding scheme. So I will first create a codebook. I I have the weight is like 2 to n r, right? So I set the weight, oh, sorry, weight is r. So I have like, so therefore, like when I use the channel n times, I will have m equal to 2 to n r, just as what we want. So I have 2 to n r messages that we can send, like when we use the channel out n times. So then we need to design the code book such that like I will, what I'm going to design the code book is very simple. I will have just get a marginal distribution px from pyx here, or like we can, okay, basically we pick the px that is maximize the capacity. And then I'm just going to sample sequences, m sequences from this distribution. So I have like, let me just call it like xn1 up to xnm, right? I just draw the sequence, I mean, draw sequences m times. And at the decoder, like decoding, so, okay, encoding then will be very simple. So each of them will be the code word. So if I have like, my message is 1, then I will just send this guy, right? If my message is big M, then I will search this guy. So this is encoding, right? Simple, simple, simple. So decoding is also very simple, theoretically speaking. So for decoding, I will basically have, I will receive a YN, right? At the other end of the channel, I receive YN there. Now I will just basically go through each of the code word from xn1 up to xnm. And I'm trying to see like which one will be jointly typical with this guy, if what I send. So I will basically will look for xn I, or like maybe I say like xn m hat yn. I try to look for this to be jointly typical. So m hat can go from 1 to big M. So I just look for each code word, one code word at a time, and I just check like whether each of them like is typical with yn. So if I find the xm, this m hat here is jointly typical with yn, then that's good. Like I would say like m hat is my decoder message. But I may have error or decoding failure. For example, if I have more than one code word that is jointly typical with yn, then I cannot say like which is which. So then I will decode failure. So I will decode failure if more than one m hat such that xn m hat yn are jointly typical. It's a condition that may lead to decoding failure. And that's it. That's it. Basically, that's it. Any questions with the setup? So it's actually pretty simple. So we design the code word is just, the code word is just randomly drawing sequences from this marginal distribution. Basically, this px that maximize the capacity. So we have the capacity is like maximize px ixy, right? So and the px that maximize this ixy will be this px here. I will drawing from this px here, and then I have this code words, and then again encoding will be just as sending the respective code word. I'm decoding. I'll just see like which one is jointly typical with the code word. I mean, for what we receive yn, I will see which of the code words jointly typical with yn. And then like if I have multiple of the code word jointly typical with yn, then I will just declare decode failure. Otherwise, then of course, that's also check. Okay, another decoding failure actually I didn't mention is like if none of them, right? That's obvious. None of them jointly typical. Jointly typical. equal with y. So now let's look at like the analyze this error probability, the probability of error. So probability of error will be bounded by several different cases, right? Again, I will use the Euler bounds. I can say like this cooling failure case 1, right? And I have like fail. Actually, yeah, just put 1. I have a P E1, right? And I will have like two. Let me don't write this. Actually, this is actually not really quite, because I can find a superset that include this guy. I will have error. So this is a error event 1, basically E1. This error event 2. Error if x and m, y and are not jointly typical. So this will include my earlier error event, because if this only when this is not jointly typical, then I won't find any coverse is jointly typical with yn. So if this is fine, right? If I don't have this error here, then I will have m is the jointly typical, the original m. Okay, so by the way, m is this here, is the original message. Oops. If I have this, oops. Okay. So if I have my original m is jointly typical, sorry, the covert of the original m is jointly typical with yn, then we are fine. So that's basically the two errors cover everything. So then therefore probability of error is just basically the sum of, is bounded by the sum of these two. It's just a union bound. And first of all, the second one it goes to 0, right? Because as we said, like if we are pulling sequences from a joint source, think of like what we have here. If we are sending x and m here, right? I'm sending x and m here, and x and m is drawing from a px here, right? And then afterward, this x and m is going for a py given x to get this yn, right? So then if you think of that like this thing here, maybe I write like this. This thing is actually a joint source of pxy. Yeah, because you have, that's nothing different from like a joint source of pxy. So therefore, like for these two sequences drawing from a joint source, then they just have to jointly typical. So therefore, like the probability of these guys, P2 will just go to 0. In other words, like they will, everything, like whenever I'm drawing that, like it will be always be jointly typical. So for error 1 here, it's basically just using our packing lemma, right? So if remember the packing lemma that like as long as the number of let's see, that's basically m here, right? As long as the number of coverts here is less than 2 to nixy. If m is less than 2 to nixy, then this will go to 0, right? This is like from packing lemma that we just discussed earlier. So that essentially means that like our weight, as long as our weight is less than like ixy, then we can ensure that the probability of error can make arbitrarily small. So of course there's some epsilon and so on, but that's not important because the epsilon is depends on the epsilon. You can fix whatever epsilon there, but as long as you increase the n there, you can always ensure that like the probability of error will be going to 0. So I guess that's it. Actually, that's basically the forward proof. There's some a little bit sketch and there's a little bit tiny technical detail, but I don't think I'll go into that. So, but if you're interested, like, or like if you want to, yeah, but don't worry about that. Like if you, I mean, if you read the notes, there's some technical things like that I didn't mention here that, yeah, it should be fine. But yeah, so this is the forward proof. Any questions for that? For the Converse proof, I guess maybe I don't have time like for the whole thing, but I just say the key step here. The Converse again is like I want to show that like if my probability of if my weight is larger than the capacity, so maybe larger than xy, let's say larger than the capacity, then my probability of error will basically non-zero. My probability error will go to will not be 0. And we can kind of tackle this in a very similar manner that we did for the source coding theorem, like with site information. I don't think I go for the Converse proof for source coding theorem, but I go for the Converse proof for source coding theorem with site information. Actually, that one is even a little bit more complicated. But it's basically like the same thing as there. Here we are instead of trying to show this guy here, we'll say if the probability of error go to 0, we'll look at a different, trying to prove a different statement here. If probability of error is equal to 0, then we will show that the weight will be less than IXY. So we cannot have weight less than more than IXY. So to show it there, like we need to have like 2 steps. So one step is like we derive a Fano's inequality. That's like something that is saying that if I have yeah, the Fano's will be something like that. Let's see. If we have the decoder, I probably have an n here. Then the conditional entropy like that will go to 0, something like that. This is again a very intuitive argument, right? If probability of error go to 0, if probability of error is equal to 0, then I just look at the decoding. I just look at the receive message from the channel the channel output there. Then of course I can recover the original message, right? So if the probability error is equal to 0, therefore like the conditional entropy there will be equal to 0. And with that, then we basically can show that we can show this guy. Should I show that? Actually, I have 0 minutes left, so so are you guys still here? I guess I will just take a roll. Okay, at least someone responds yes. So okay, okay. So I guess I will take 10 more minutes. Then I guess it will be done. So let's see. Let's assume this Fano's actually. for the Fano, I have okay. How do I show Fano? Okay, let me look at cheat sheet so it'll be quicker. Otherwise, I will take more time, I guess. So for the Fano, I will just start defining something like the error event. The error event will be like just an indicator saying like m if not equal to m hat. So maybe I use capital M instead. So this is assumed to be like random variable as well. So this is an error event. Then when m is not equal to m hat, that is the error. And then I can write hm given yn. That will be equal to hm e given yn minus he given yn m. So what I'm doing is just basically chain rule. If you move this other term here, then you see that it's equal to hme given yn here. And then like from here, know that like if I'm let's see, note that this guy is actually just equal to 0, right? Because I given yn here, if I have the given yn here, then I can decode back like m hat, right? So I have m hat and m, then I know whether the error happens. So therefore this is equal to 0. And this guy on the other hand, I can like expand the other way. It will be he given yn m. Or like maybe he given yn plus hm given yn here. Okay. And then like this anyway will be less than equal to 1, right? Because this is just binary. This is less than he because you have conditioning, you reduces entropy. Me is just binary. It's either 0 or 1, right? Either true or false. So therefore, this is less than equal to 1, right? And for this guy here, I can write it as the I split into like two different cases. Like probability that like e equal to 0, hm given e equal to 0 yn plus probability e equal to 1, hm given e equal to 1 yn, right? Now, when I don't have error, so if this is equal to 0, like p equal to 0, meaning say I don't have error. If no error, again, like this will be equal to 0, right? Because with yn, I know m hat here. If no errors, then m hat is equal to m. So therefore, this one is gone. So I only have this term left. And this p probability e equal to 1, this is actually just equal to the probability of error, right? It's equal to probability of error times m given this thing here, right? E equal to 1. And anyway, this thing is less than hm. I can say just is less than hm. So I will have I've like this. And if I put 1 over n back, then I have 1 over n. I mean, if I divide divide n on both sides, then I 1 over n hm given yn is less than equal to 1 over n 1 plus probability of error hm over hm anyway. So the point is if n, okay, I can put maybe like 1 over n and hm over n, something like that. This thing here will be finite. It won't be infinite. And if your probability error goes to 0, then this will be gone. So therefore, n again, if n goes to infinity, this will be gone. So therefore, the whole thing will go Yeah, actually, I don't. This will go to 0 basically as n goes to infinity. But typically, like the Fano inequality will be y like this. So it's just like the Fano's y like 1 over n 1 plus hm, something like that, or something similar to this. But the point is like if you have, oh, okay, I missed the PE. Sorry again. But the point is that like if probability error is 0, if n goes to infinity, then this thing will go to 0. So now then we can prove the converse with the Fano's inequality. So this is Fano's again. Like this is Fano's basically. Fano's is just saying that okay, if probability error, oops, actually, I better also circle the condition there. So now for the converse proof, basically, we say the probability error is equal to 0. Then let's say the weight is given by like hm over n, because you have the message, right? The amount of information sent through the channel is just hm. The weight will be like the amount of information sent per channel use rate. Therefore, I need to over n, right? So, and this I can expand as 1 over n I m y n plus hm given yn. This is just expanding hm here. And this will be less than equal to, so this guy, this is, we're using this data processing inequality because we have this Markov chain here, m, and then generate this xn, and then I have yn here. There's a Markov chain here. So therefore, like visual information xn and yn is bigger than equal to visual information between m and yn. So therefore, this is like less than equal to ix and yn plus hm given yn. And then I can expand this guy, hyn minus, this is hyn given xn, right? Plus, okay, this term I can just forget about it, right? Because this is will go to 0. If probability error using Fano's, this will just go into 0. So let's forget about this. So I only have these two terms here, right? And yn here, by the way, this will be less than equal to sum of hyi, right? So this is, or maybe let me just write like this first. So this term is using chain rule is equal to something like that. But then I can remove conditioning. So then therefore like this. So therefore like this guy will be less than equal to sum over hyi here. And for this one here, again, I can use chain rule. So the chain rule will be like sum over hyi xn yi minus 1, right? Now, but we have Markov chain here because our current, okay, sorry, I have the index to be below. So if you look at the I output here, like you have a channel, you have this yi here, you have this xi here. This channel output, knowing the channel input actually does not depend on anything else, right? It does not depend on like the previous inputs or like the future outputs and so on. So therefore, like given like xi here, this xn here includes some xi here. This xi and x not I, let's say. given this xi here, the rest is actually like all redundant. So therefore, like this would be like actually equivalent to hyi given xi. So this becomes just like that. Then we are already done, right? So we can regroup this term. So I have hyi given x. Sorry, this is just I x. Yeah, xi yi. Sum over I equal to 1 to n over n. Right? I'm sorry, sometimes I use big N, sometimes I use small n. They should be all small n actually earlier, right? Because I copied from the notes there, I'm using big N there. And because it's ID of these are the same, right? So therefore, you have n of them, some of them together, and over n would be the same thing. It's just ixy, right? So therefore, like we're done. Actually, the converse is done. So when the error is equal to 0, right? Then your weight will be basically less than equal to ixy. And I guess that's it. Yeah, I have 10 minutes over time, not too bad. So I guess after the quiz, we'll just not the quiz, the midterm, we'll cover something new. Yeah. And again, like the solution is on Discord. Like if you never been to Discord, be sure like at least go there and capture the homework solutions or download the homework solutions. And also like if you have any questions like regarding course materials and so on, you can put it on Discord as well. So yeah, it's much better to contact me like through Discord. Like sometimes I miss out emails very easily because there's just too many junk mails. So okay, what do you say? I see. No, I didn't upload to Canvas. I just put on Discord. Do you know Discord? Yeah. Yeah. So yeah, if you guys have any questions, also put it on Discord. So I will look at that. Like at least I will reply once a day. So yeah, most of the time I'm much more. Yeah, I kind of like check Discord much regular than like a couple of times a day. So so any other questions? If not, I will just stop here. Yeah.
Can you explain the question 2? I didn't get that.
Say that again.
Can you explain the question number 2? I didn't get that.
Oh, wait, I need to go back. I forgot that was question number 2. Wait, I think I probably, did I erase that? Let me see if I have it here.
I think this is the one.
Yeah, I think I already erased that, but you can see somewhere. So it's the packing and the covering lemma. So the question number 2 is saying that like what is the number of let me just write it down. So basically packing. I think I asked the covering lemma, but it's basically the same thing. So the question is something like I'm drawing from like 2 independent source here. So I have xn, yn. So they shouldn't be jointly typical by default, but if I draw enough of them, eventually they will be jointly typical, right? The question is like, how many of them are needed until x and y and it, I shouldn't say that, until some of the pair are jointly typical. So here basically we have 2 to n, the solution to the answer is 2 to nxy. It's like we have a half threshold there. So if we draw like enough of them, like more than 2 to nxy, so there will be always some pairs will be jointly typical with one another. So, but if I draw less than that, like that, the probability for any of them to be jointly typical will be equal to 0, and that would be like what is addressing the packing lemmas. Basically saying, if I have the number of pairs I I've drawn is like less than 2 to nxy, then none of them, I cannot find any of them to be jointly typical, or the probability of any of them to be jointly typical will goes to 0 as n goes to infinity. So any other questions? So if not, I will just stop here, and then I just feel free to contact me, and so, and put any questions there on Discord, like if you have any questions, and see you guys next week, and good luck. Yeah. Bye now.